Hello. We now turn our attention onto eigenspaces. I just need a second. I need a little bit of coffee sometimes. So, eigenspaces are going to be vector spaces directly related to eigenvalues and eigenvectors, and very neatly, they inherit some properties from the general theory of a vector space, and more importantly, they inherit properties as a subspace. But this is a direct connection between all we have learned from definition of vectors of a vector space and the definition of a subspace. Direct connection of those concepts, of those theorems, with this new topic that has to do with eigenvalues and eigenvectors. So let's refresh our mind and about the definition of eigenvalues and eigenvectors. So we're working with a matrix that has n rows and n columns, right? So again, this matrix is a square matrix, and we are referring to an equation that has on one side a matrix vector multiplication, and on the other side of the equation it has a scalar multiplying a vector, and these two things are set equal to each other. Therefore, we're referring to scenarios in which the matrix is a given matrix, and then such scalar and such vector exists. So we have to think of this vector and that scalar as some kind of team or companion. They are teammates, right? Or they are companions of each other. And so they come together even though one of them is a scalar and the other one is a vector. They have very different dimensions, if you will. And so here is a refresher of what it's involved in the calculation of such scalars called eigenvalues and their companions, the so-called eigenvectors. So first, we define a polynomial that is going to be a polynomial defined with some letter, some letter that we choose for the variable in that polynomial. Let's say we're working with t, so we're interested on subtracting that variable, the polynomial variable, from the diagonal entries of the given matrix A. So that gives us a new matrix, and that's what we write as A minus Ti. And then we compute the determinant of that new matrix A minus Ti. And that's what we call the characteristic polynomial. So the so-called eigenvalues are roots. Those are the values of the characteristic polynomial at which the polynomial becomes zero, typically called zeros of a polynomial or roots of a polynomial. Those are the values we're interested in. Those lambdas are exactly the same lambdas that appear on the eigenvalue eigenvector equation there. And so those are the values we're interested in. Because we're working with a n by n matrix, then this is some algebraic theory. So polynomial of degree n has exactly n roots, and each of those roots is an eigenvalue. So there are n eigenvalues for this square matrix that is n by n. So that result of having n eigenvalues allows for repetition. These eigenvalues could be repeated, or they can all be distinct, different from each other, but we will count them as n, the number of rows and columns. And importantly, because of construction and the way we're working with this calculations, is that this matrix, when evaluated, remember we were working with A minus Ti. If you choose another letter, you could write something like A minus Xi, or we could write something like A minus Si. It doesn't matter. This is the letter T, X, S. Whatever variable you choose, that is a variable in which you write the polynomials, something like T cubed, I don't know, plus T squared plus T plus 1. That's a polynomial of degree 3. And you could write the exact same polynomial with different variable like x3 plus x squared plus x plus 1, or s3 plus s squared plus s plus 1. So they are all representing the same polynomial. They have the same powers, the same coefficients. This is just this is an example here to kind of make the point a little farther. These are three representations of the same polynomial, but they all use a different variable, a different letter. Okay, T, X, S, whatever you choose. And so, importantly, when you evaluate that matrix A minus Ti at each of those lambdas, the new matrix A minus lambda I, this matrix A minus lambda I, is a singular matrix. And so singularity is directly related to the definition of a null space. The null space, remember, is a solution set of a homogeneous system of equations, and a null space that has, in addition to the trivial vector, in addition to the column of zeros, the null space will be a solution set for a homogeneous system if it contains non-trivial solutions. And if it contains infinitely many of these non-trivial solutions, then that's what we call singular. We are directly related to the definition of singularity. A matrix A minus lambda I that is singular is going to have a non-trivial null space. And so the key here on the last step of this recipe for calculation of eigenvalues and eigenvectors is to compute the null space, but really we want to compute a basis for the null space, right? And this goes back to what we had learned about calculation of solution sets. We need row reduction, we need to compute R, we need to compute N minus R. N minus R would be the so-called nullity, the dimension of the null space. So the nullity of A minus lambda I will be given by N minus R, and this is exactly how many elements there will be on the basis that we compute for the null space. And from that basis, then we can build eigenvectors that are associated with the particular lambda value that we're working with. So we have a definition for an eigenspace, and such space is going to be defined relative to a specific value that we call eigenvalue. So suppose we have a square matrix A. Suppose that also that lambda is an eigenvalue. So we have something like A times, I don't know, W equals lambda W. Right? So that's what we mean by suppose such lambda and such vector exists. Then an eigenspace, the eigenspace of A for lambda. So we have to use this term eigenspace, we need to specify the matrix in question and the eigenvalue in question. So the eigenspace for A of A for lambda is denoted here. This E, this funny E, this is called epsilon. It also looks like the symbol we use to say that something belongs to a set. So, but this is going to have a subscript where the matrix is denoted, and then there is an argument here in parentheses. So here we write the matrix, right, in the subscript, and then in the argument we write the eigenvalue. That's the idea, okay? The eigenvalue. This eigenspace, denoted as E sub A of lambda, is the set of all eigenvectors of A for that specific lambda. And together, includes all the eigenvectors of A for that specific lambda added to or together with the inclusion of the zero vector. What happens is that the zero vector is kind of a trivial eigenvector for any. So obviously, if lambda is 0, and here we assume that we're working with A being a square matrix. So if lambda is 0, then A times 0, this being the zero vector, this here being a vector in Cn, A times 0 is the zero vector in Cn, okay? If we're multiplying a matrix times a zero vector, we will obtain the zero vector. And the zero scalar times the zero vector, I'm using that physics notation that has that symbol there on top. This is indeed the zero vector, right? So this still is in Cn. So the matrix times that vector of zeros is equal to the same thing as if you multiply the zero scalar times the zero vector. That still is a column of zeros. So both of these things are equals. When lambda is zero, the zero vector is an eigen vector. But also if lambda is not zero, if lambda is not zero, you could consider multiplying a times the zero vector, that is the zero vector, but also lambda being a non-zero scalar multiplied by the zero vector, that is also equal to the zero vector. So even for non-zero eigenvalues, the zero vector is always a trivial eigenvector, if you will. So that's why it's important here to remember that this space epsilon a of lambda is considered a space, is considered a set that contains the zero vector, since the zero vector is sort of a trivial eigenvector. And now this theorem tells us, suppose we have a square matrix of size n, lambda is an eigenvalue of that square matrix. The eigenspace E sub a of lambda is a subspace of the vector space Cn. This is a big deal, okay? And this is beautiful and it's a big deal. Maybe you don't believe me it's beautiful, but it is super cool, okay? So let's see why. So remember that if we are considering A multiplying some vector W, so we're saying A is n by n, and we're assuming this vector W is, excuse me, this vector W we assume is n by 1, right? So when we do this matrix vector multiplication, we end up with a one-dimensional array of numbers here that is n by 1, okay? So if, in addition, that vector W is such that lambda times W equals A times W, right? In addition, if this is something that equals to scalar times vector, then we're gonna see that these vectors, when collected, right? When collected into, so here we would say that W would belong to E sub A of lambda. So this set, E sub A of lambda, is a set that contains such vector W, and since each W is a vector with n entries, this set would be a subset of Cn. So when you think or collect all those eigenvectors into a set, they are collected, that subset is, that set is indeed a subset of the vector space Cn.